went through the simple way of solving how much weight we're lifting in a push-up just by using a couple of scales. But there's a more technical way you can get to something like the same conclusion and explain why that is the case mathematically. So let's try and go through that. So our problem is we've got me doing a push-up. I want to make me rather large, kind of here, right? And let's say the floor is something like that. And the question is, how much weight have I got in the hands versus how much weight have I got in the feet? Well, the first thing we know is that my mass is pressing on the floor. Okay, so let's say my mass is going to be 95 kilos. And we know the force of gravity, right? So the force of gravity, we're going to say, is roughly 9.8 meters per second squared. And the first thing we're going to need to know is that it has 2 points of contact with the floor. So we're pressing, that whole mass is pressing down where I meet the floor, in this case the hand and the foot, or the hands and the foot. Well, am I going through the floor? I don't appear to be going through the floor, which means there must be an equal amount of force holding me in equilibrium and stopping me being accelerated through the floor at that pace. And so we have a ground reaction force, which we could write as GRF, but we're going to write as N, which stands for the normal force in physics. That's generally what that's written as. And we have N, it's applied at the hands, so we're going to say N sub H, the normal force at the hands. And then we also have the normal force at the foot, N sub F. But where's my mass being pushed down from? Well, whenever we have these problems, we need a center of mass, okay? And the center of mass, you can look up online and find out actually where it roughly is in a human being, because it varies. If you've got slightly bigger arms or slightly smaller legs or a slightly bigger stomach or whatever, your center of mass is going to move to reflect those things. So it's not static and it's not the same in everyone. But we're going to say that it's roughly around here for me, okay? And so where this force is applied is at the center of mass. So the force of this is applied right here. So the force that these two things are fighting is that applied at this point. And so we're going to call that force F at the center of mass. F sub cm, center of mass. Okay. And we know that we're in equilibrium. So the force of the center of mass must be equal to these two forces together, right? N sub H plus N sub F must equal the force at the center of mass. That seems pretty obvious, right? Because we're not moving, so fine. But this doesn't tell us how much weight is in N sub H or N sub F. It just tells us that this number together is the same as that number. If that number is 10, then these together add up to 10. But I don't know whether there's 8 and 2, 5 and 5, 7 and 3. I don't know, and I can't know from this. The way we're going to solve this is by understanding these as a torque problem, or the sum of moments of torque, which sounds super complicated. But let's remind ourselves of torque. So torque is written with a T that looks like that. Torque is equal to a force, which we actually have here. In fact, we have 3 forces. And its perpendicular distance to an axis. So we're going to write perpendicular distance like an upside down T, because that is perpendicular. You might also see it written as FR, where R stands for the radius or the moment arm. It's the same thing, it doesn't really matter. Well, we've said F is equal to MA. Who remembers their Newton? Let's put this over here. Force is equal to a mass times an acceleration. Well, that's what we've got here. So there's a mass, that's the acceleration due to the gravity on Earth. So we have, for this, the torque of something that we're going to calculate in a second is going to be equal to mass times the accelerative force of gravity times its perpendicular distance to an axis. Okay, so we could write this as mg perpendicular. So our torque is going to be that, depending on which one of these we pick. But I've just said, okay, so we've got a force and a perpendicular distance, but we need an axis, otherwise there's no rotation. So we could pick any of these as our axes. We could spin around the center of mass, we could spin around the foot, we could spin around the hand. Doesn't matter, you'll actually get the same numbers whichever one you pick because they add to the same thing. I'm going to use the hand. So let's assume that the hand here is held in place. It's magnetized to this point, it's bolted in place, it's stapled there, I don't care. It's just not moving, okay? And so now we have two forces applied at a distance from an axis, and that means they create torques, they create rotation. So this force, applied like this, is trying to create rotation that would want to go in that direction, okay? And this guy would be wanting to do the opposite. He's trying to rotate that around this guy, so actually that would need to be bigger than I've drawn that, but you get the idea. One is creating rotation in this direction, the other one is creating rotation in that. Well, am I rotating? No, I don't appear to be rotating. So just like the forces sum to zero, we must say that the torques sum to zero. And we've got two torques. This is now our axis. So the normal force applied at the axis provides zero torque because, well, remember, torque is equal to a force times a perpendicular distance. What if there's no perpendicular distance? Well, then there is no torque. There is just a linear force. So no torque, so we can ignore that. That's now our 0 point. So the torque provided by the force from the center of mass, so T, F, sub Cm, which is, I'm going to write that, so the torque provided by that force, plus the torque provided from the normal force on the foot, must equal 0, because I'm not going anywhere. If I was going somewhere, that wouldn't equal 0. Well, if we have a number plus another number and it equals 0, what does that tell us? It tells us that that is the inverse of that. You know, 5 plus what equals 0? Minus 5. Minus 5 plus what equals 0? 5. So whatever one of these we denote as the positive, we know that the other one is the opposite. So we could also say that the torque from the force at the center of mass is equal to the inverse of the torque from the normal force. That's a terrible T there, but you get the kind of idea, right? So they're the same number as each other. And because we know that T, wherever we see T, we could sub in F, perpendicular distance. And because we know the force we're dealing with is coming from gravity, wherever we see F, we could sub in ma, and our accelerative force in this instance is gravity. So we're going to sub in, instead of T here, we're going to put mg, perpendicular distance. So let's say the mg perpendicular distance of the force from the center of mass is equal to the mg perpendicular distance from the normal force. And that's the same as saying those things. So we haven't said anything different. Well, what do we know so far? We know this guy, okay? We know at least mg, right? So mass is 95 kilos times 9.8 meters per second squared. Then we're going to need to know this perpendicular distance. So we're going to have to give these some numbers. So let's give them some numbers. I don't think I've actually drawn these ratios quite right, but for the sake of making this simple for us to follow, let's assume that this distance here is 0.5 meters. And then let's assume that this distance across to there is 1.5 meters. So we've got a force applied at a distance, a perpendicular distance, that's perpendicular, of 0.5 meters, and another force applied at, sorry, I should put this through here, that's not clear, 1.5 meters away from that axis, not from the point of the center of mass. It's 1.5 meters away from here, not from there. So now we've got two things. Okay, so this guy, the torque from the center of mass on that axis, is equal to 95 kilos times the accelerative force of gravity times now its perpendicular distance, which we've just said is 0.5 meters. And we know that that is equal to the torque being provided by this. Well, we don't know what NF is yet, so let's leave that as just NF, the force from NF. But we do know its perpendicular distance. We've just said that's 1.5 meters. So something times by 1.5 meters is equal to the sum of that equation. Well, that means we're trying to get N sub F just by himself. And we can do that quite easily. Now, I don't know how familiar you guys are with rearranging algebra, so I'll walk it through from the basics on this. If we had a number, let's say this number was 6, and we timesed it by 6, what would we have to do to get back to 6? Divide it by 6. So if we take this number here and divide it by 1.5, those two numbers cancel out and leave us with N sub F. But we've got an equal sign. And that means this thing must be exactly the same as this thing, otherwise it's not equal. So if we do something, anything to this side of the equation, to keep it equal, we must do the exact same thing to the opposite side. So let's do that. So I'm going to divide this by 1.5 meters. And so now on this side, they cancel out. So mass times gravity times a perpendicular distance divided by the perpendicular distance of the other force leaves us with the force from the normal force on the foot. We could rearrange this a little simpler because we've got 0.5 meters divided by 1.5 meters. And there's a ratio between 0.5 to 1.5 that is a third. So we could rearrange this and say that 1/3, and these two were just mg, mass times gravity, 1/3 mass times gravity is equal to the normal force on the foot. And now we know that if the sum of the torques must be 0, and we also know that the sum of the forces is 0. So now we have this force, which we'll write in a second, is going to be equal to this plus this. Well, now we know what this is. So now we could say that this and this together in some way are going to leave us with that. In other words, if I take away F, center of mass, minus what I know is the normal force from the foot, I'm left with the normal force on the hand. So let's say we knew that this was 10. NH plus NF equals 10. Well, let's say now I know that NF is 3. Well, if I take 10 minus 3, what am I left with? 7. That must be the force that's left over in that because we knew we were in equilibrium to begin with. And so if 1/3 mass times gravity is the normal force on the foot, then 2/3 mass times gravity must be equal to the normal force in the hands because the sum of those two things must add all the way up to mass times gravity. Those two together must equal, so let's just put a plus in between them, must equal F, center of mass. And they do, because 1/3 mass times gravity plus 2/3 mass times gravity equals mass times gravity, and the force we've said is mass times gravity. So that all works. So finally then, let's figure out what those numbers actually equate to. No one wants to have to do this maths in their head, so we're going to use a calculator. But let's go 1/3 times 95 times 9.8 equals, so the normal force on the foot, let's put this over here, NF of the foot is equal to 310.3 recurring, and that's measured in newtons, and newtons is kilograms per meters per second. Okay, we call that N. That's a force, by the way. If we want to come back to how much mass, technically, is in my hands rather than what's the force on my hands, we can do that really simply by rearranging FMA in a second. But let's just get the second one as well. So this one is now equal to 2/3, which is going to be equal, so this is the force in the hands now, is going to be equal to 620.6 recurring newtons. Now we've got a force here, but we want to bring that back to a number that's related to 95. So we're going to need to go back to F equals MA. We want to get M left by itself. So we're going to have to get rid of the A. So we're going to divide this side, acceleration divided by acceleration. This number times 9.8 divided by 9.8 brings us straight back to M, which means those two cancel each other out. But we had an equal sign, so that means we must have done the same thing on that side. So if we take the force, these numbers, and divide it by the acceleration, we're going to be left with the mass. So F divided by A equals M, and that's going to tell us how much weight. Technically weight is a force, and it is that force together, but we started with understanding 95, so we'll stick with that and assume we know what that means. How do we get back to how much mass is in the hands versus in the foot? So all we're going to do is take 310.3 for the foot and divide it by gravity. So if we have 310.3 recurring divided by 9.8, we are left with, so the normal force at the foot is equal to 31.6 recurring kilos. And so the normal force on the hands is going to be the same thing, but 620.6 divided by 9.8 is going to be equal to 63.3 recurring kilos in the hands. And if we add those guys together, you'll notice that they come to 1.1 of 95. The reason they come to 0.1 is just these rounding errors. Okay, but it gives us the exact same number. So the reason that we lift the weight we lift in terms of what's in the hands versus what's in the foot in a push-up or any problem like this is related to the distance the center of mass is away from those points of contact. If this center of mass was closer to here, it would be equal. Or if it was bang in the middle, it would be exactly equal. If it was closer to the foot, we'd see this reverse. When you start doing an inclined push-up, your center of mass moves in this direction, which puts more of it into the hands and less in the foot. When you do the opposite and incline further, your center of mass moves closer perpendicularly to the feet. And so more of it is supported by the feet and therefore less in the hands. And so you could just use the scales in order to figure out how much you're doing with a push-up, or you can start to understand why the scales give you the answer they do.